It's a great pleasure to start the conference with Nicholas Beisert from ETH0, who will tell us about Yangian symmetry for twist-deformed n=4 gauge theory. Please.
Okay, but before we start, I'll tell you that this talk is protected by code. So I'm afraid we have to go through a bit of a Rumpelstiltskin exercise. So what do you think the code is? 4-digit code. Say the word. No. Wrong. Dead. 2 more tries left.
1, 2, 3, 4.
Nope. Sometimes it's a date. And
2902 or 0229?
29, no.
2902.
No.
That's sometimes a date.
That's a paradox. What could be the date?
15.
Oh, yes. Okay. Now you've unlocked the talk. So thanks very much for the invitation. It's very nice to be back in Stockholm. And first thing for this conference, I should probably wish us all a very interesting conference, except that that wouldn't quite be too proper for me to say, because actually I have to leave today to get back to my teaching, or to get my teaching started. Central Europe is a bit far away, so but anyway, I wish you all a very interesting conference. And so let me start with my own talk, which is on Yangian symmetry, and what's the topic of the conference. This is about twist-deformed n=4 gauge theory, and it's work that has been doing for quite a long time with Benedikt König, and haven't really come to a conclusion on all the things, at least on the things we wanted to start with, namely to get some insights or new insights on fishnet theories. But anyway, we've discovered interesting things along the way. So let me try to give you an overview of or the setting of our research, which is about Yangian symmetry. Yangian is as you probably know, or at least superficially, is a quantum algebra which is behind integrability. There are also other quantum algebras, but here I'm in the rational case, XXX, so I'm not touching on quantum affine or something similar. So this is only about Yangian. And this Yangian algebra has been established by DSDF integrability in various locations. The first time I think it appeared was in this paper by Dora and Napi-Witten on the one loop n=4 spin chain. And there it somehow governs the R matrix, the beta ansatz, but also the bulk Hamiltonian. It's not typically a real symmetry of the spectrum. So in that sense, it's only a bulk symmetry of the spin chain. Boundaries somehow break this Yangian symmetry, which is also some issue we will always have to deal with. But nevertheless, since it's some organizing principle, it would be good to understand whether this, or it was good to understand whether this Yangian symmetry really exists, not just at the one loop level, but at all loops, at finite coupling, and also in string theory, where this is also not fully understood, as far as I would say. One way to understand this Yangian symmetry is that can be seen as the closure of conformal or superconformal algebra, or the sigma model space target space symmetry, and a dual set of symmetries, which in string theory arise from T-duality. Now, this Yangian symmetry, as I say, acts as a symmetry to some extent for the spin chain, but apparently to a larger extent to the S matrix, at least up to the divergences that you get there. The infrared divergences are a problem there. Okay. Even before that, Yangian symmetry also, Yangian algebra also arises as a symmetry for the worldsheet S matrix that is behind all this business of quantum spectral curves. yeah, as I said, it's there for scattering amplitudes. You can also see it for Wilson loops and for correlation functions. It acts in a very specific way, which I'll show on the next slide. And then sometime later, we've also seen that you can write this as a symmetry of the classical action of n equals 4 superiorinals. And it also survives quantum effects. So that might be a good hint that this is really the true symmetry of the model, even though it's not a symmetry of the spectrum of local operators. Now, in this talk, I want to talk about Yangian symmetry for deformed models. The three questions I really want to address is how to apply this Yangian to twist deformed models. That is, twist deformed models for me will be beta or gamma deformed models, or Grünfeld-Reshettikian models, or Billion twists. There are various names for this, but you understand what I mean. And in trying to address this question, we first had to understand a bit better what is this Yangian symmetry, and how does it really act on the gauge theory model. And at the end, I would like to address fishnet models as far as I can. So the overview will be that I start with just explaining a bit what is Yangian symmetry and n equals 4 gauge theory. Review the twist deformation and integrability of it, and then revisit this Yangian symmetry in a somewhat formal way, where form means variational or differential forms. And then once we've understood that, it's actually a neat formalism to address symmetries. We can turn our heads to twist deformations, which then work quite in a straightforward way by basically twisting everything you want. And at the end of the day, we can turn to fishnet models as a limit of these twist deformations and see whether or not there is Yangian symmetry for these. So yeah, the Yangian is a Hopf algebra. Just let me give you a very lightning review of how this Yangian works. You can see it as generated by two copies of the underlying Lie algebra for your model, that is PSU 2,2/4, or say in more simple spin chains at PSU 2. So two copies. The level 0 copy is just a plain Lie algebra of the symmetry, so there's nothing very unusual about it. And the level 1 transforms in the adjoint of the level 0, so it behaves much like it, but it also obeys certain relations that I mean, these are just the ordinary transformation rules for level 0. These are the level 1 adjoint transformation rules, and then there are some Serre relations which I don't really need to go into here, but they constrain this algebra and reduce it to the simplest part of it, the smallest part of it. Now, this is a quantum algebra, and you also have a coproduct, and the coproduct describes the action on tensor products, which you would need for defining spin chain representation on spin chains. And the level 0 generators just act as usual. They act like a tensor product rule. They act on all the sides of your spin chain individually and one at a time. But the level 1 generators will act bilocally, in the sense that you act on two sides of the chain, and now you have also two copies of these adjoint indices, and those you contract with the structure constants of the algebra. There may or may not be some additional local contributions, which you could view as sort of a short distance limit, or some counter terms for what happens, or contact terms for what happens when these two sides are just the same, or very close or the same. Now, there's one generic issue, which is that this bilocal thing here is ordered. You need an ordering because the structure constants here are antisymmetric, and if you sum over all sides, this would of course sum itself to 0. But so you need a certain ordering here, but the ordering is not compatible with cyclicity of spin chain states that you normally have. And normally that prevents you from acting with the Yangian properly on states, but in certain situations such as this one, there always just has been a way around to make this work. Not really going into this, but that has been quite well understood so far. Okay, so let me try to address this. I mean, this symmetry works in a plain way for ordinary spin chains. Let's try to apply it to twist transformations. But first of all, what are these twist transformations? Well, oh no, maybe I should first discuss the the setup for these theories. So you have n=4 super-Mills action, and the symmetry, the level 0 symmetry is just a conformal symmetry which acts on this action. I'm only going to sketch the terms in the action here without proper coefficients. And now the ordinary conformal symmetry acts on one field at a time in this product of fields, in this action polynomial. So you pick any of the fields and you act with the symmetry on it, and then you sum over all possible fields in this polynomial. It is, however, what is sometimes called a nonlinear representation, in the sense that a field may transform to not just one field, but it could also act to transform to any product of fields. And this is not a problem, because here you're within polynomials, and once you transform one letter of the polynomial to another polynomial, it still remains a polynomial. So in that sense, it's still a linear representation, but in terms of fields, it's called nonlinear. That adds a bit of complication to the whole business, and you can only get invariance if you apply cyclicity of the trace. Here you actually have a trace, and also the integral is somewhat of a similar animal. You know that total integrals will integrate to a boundary term, and we don't care about these boundary terms. So if you have an invariance of the action, you can also come up with an invariance of the equations of motion. Here I write the equation of motion terms with this funny accent notation. So you act with a okay, this would be the equation of motion for the scalar field. So this is that term, and the equation of motion says that it's 0. And the invariance means that once you act with the symmetry on the equation of motion, you get other terms which are also like the equations of motion, and once you're on a shell, this whole combination is 0. So these are the equation of motion for our model. This is a like 5 to the 4th with power terms. This here is again some power terms for the fermions, the Dirac term, and then okay, these are Maxwell-like equations, so you have Mills-like equations. And one thing I should also add is that it's not just I mean, when I say covariance of the equation of motion, I mean that when you act with symmetry on the equation of motion, you not only get 0, but you also know the coefficients of these three other equations, or the other equations of motion that appear. So you could just say this is 0 up to equations of motion, but in fact these coefficients are also well determined by the symmetry. So in that sense, this is a slightly stronger statement, and that is what comes out of invariance of the action. Now, this is the level 0 symmetry. How would you formulate a level 1 symmetry which acts in a bilocal fashion? First of all, it wasn't so clear how the Yangian symmetry acts on n=4 super-Mills. Well, level 0 seems fine, but bilocal terms is not so clear. Our proposal of some time ago was that we somehow reverse the logic that I presented on the last slide. That is, we start with the equations of motion, try to make sense of those, make sure that they are invariant, and then basically integrate that back to invariant statements for the action. And so now you have these bilocal terms, and bilocal term acts on two fields within such a field polynomial at the same time. but that can be made sense of. You can do that, and in a polynomial you also have the proper ordering of fields. They sort of, at least in the planar limit, that makes sense. You can read them from left to right, and then it's just the ordering that you get. But that is actually where the planar limit comes in. You need a proper ordering, and that's provided by the planar. Now, this wasn't quite enough. You had to figure out suitable local or local terms, which you could see as contact terms for the bilocal terms, to really complete the equation of motion invariance. So when you act with this, with properly adjusted local terms on all equations of motion, you get 0 at least on shell. Then next thing, we also found a way to determine what are these coefficients in front of the terms that you find here, which are all proportional to the equation of motion, but you need to know the coefficients. And once you have those, you can combine all these covariance statements, because now, I mean, if you know the coefficients and you don't impose on shell, then this will be some polynomial. So you combine each sort of variation of the equation of motion with the field itself. You do this for all the fields, you sum over all fields. As a covariance statement, this would give you 0. But we can now take this as a polynomial, take a trace, integrate over space-time, and thus get something that looks like a variation of the action. That's sort of doing this same procedure that we had on the last slide in reverse. We can also add some level 0 symmetry statements, because this is sort of, we also know that level 0 symmetries are there, so that it can allow us to give us a nicer form. But in that way, we obtained an invariance statement for the action. And that statement is a procedural way to sort of to act on the action and get something out. And if that is 0, we could then argue that the model is Youngian invariant. If it's not 0, it's not. And you could apply this to some models where you think you have integrability, like n equals 4 super Young-Mills, or others where you think you don't, and this somehow the results here match with that. So for Youngian, for n equals 4 super Young-Mills, you get Youngian symmetry. For the others, you typically don't. It's rather a lot of terms that arise, and so it's quite surprising that you can find some cancellations there. Okay, now I want to apply this to, or we wanted to apply this to twist deformed n equals 4 super Young-Mills. So we review that. In twist deformed n equals 4 super Young-Mills, you basically introduce some twist, some bilocal twist with some antisymmetric matrix, and these generators here are from the Cartan algebra. We just take SU4, just the S5 part of the model for our deformations, because we don't want to mess with the ADS5 factor. Right. So with F, you can you can also apply this to any field polynomial, as long as it's not traced, because here you have some antisymmetry again, and this requires you to have a proper ordering. And if you apply this to any untraced field polynomials, you get some funny phase factors which depend on the charges of the fields or the spin sites, and on their particular ordering. But it's a procedure to sort of twist anything that you want from the untwisted model to the twisted model, and even back. However, you cannot quite apply this to cyclic polynomials, polynomials where you have a cyclic ordering imposed on the fields, because again, I mean, here you need a proper ordering, and cyclic ordering does not collaborate well with that. However, this does work if the state you're acting on is uncharged with respect to all the charges that appear here. If it's uncharged, you can still make sense of it, and that's also what you do to twist the action of the model. So the action of n equals 4 super Young-Mills is totally symmetric, and so under the Cartan algebra, subalgebra, it's also uncharged and it's cyclic. but it can be twisted, and that gives you beta deformed n equals 4 Soviet mils for a suitable choice of this this matrix here. I will always in this talk use this beta deformed n equals 4 Soviet mils, which has n equals 1 residual supersymmetry. All the uncharged local symmetry generators then remain local, so you get from the superconformal algebra, there's a residual algebra little group SU 2.2/1 and two of the Scartan charges for the beta deformation. And yeah, it's only the uncharged subalgebra that remains a symmetry of the deformed action and also of the spectrum itself. However, you can also apply these transformations to the equations of motion, and the equations of motion are not cyclic polynomials, they are open polynomials. They have a beginning and they have an end, and you can properly twist them whatsoever. And in that sense, these even the local, even the all equations of motion can be twisted, and you find proper symmetry statements for the for those generators that have been broken in this twisting process. That is, here you break 3 of the supercharges and 3 of the superconformal charges and almost all of SU4. So that gives you a funny situation in the sense that you have a complete PSU 2.2/4 superconformal symmetry that remains as a symmetry of the deformed equations of motion. It's not symmetry of the spectrum though, but it's still there. And that's left us with a sort of funny situation, because how to twist deform the Youngian symmetry statements that we had. Ours were based basically ultimately on the equations of motion, and it seems that everything should be maybe the action is even fully symmetric. So what has been shown before by Xenagaos is that the full PSU 2.2/4 symmetry and also the Youngian invariance applies to the equations of motion. And if you use the procedure that we had, we could, in principle, try to lift that to a symmetry of the action. And that would mean we not only have a full superconformal PSU 2.2/4 action, but also a Youngian symmetric action with that symmetry. And so that would have been a bit too much, and we really had some trouble to understand why or why not this should be a symmetry. And therefore, we had to review how to deduce the Youngian invariance of the action. Now, I mean, also, even if only part of the Youngian applies as symmetry of the action, how can one really identify what is a proper symmetry for the action? Is it, and also, is that a subalgebra, and how about the co-algebra? So that's also something that we will see. The level 1 SU 2.2/1 subalgebra actually, even if you just restrict it to a subalgebra, and if you look at the co-algebra, these generators from the subalgebra require the complete level 0 supersymmetries, which is then also funny because these are not symmetries of, these are probably not symmetries of the action, but to even define level 1 subalgebra, you need them. So it's a bit of a troubling situation. And also in translating the symmetries for the equation of motion, the action, we required some level 0 generators, but some of them are now charged. And if they are charged, they are probably not symmetries. If they're not symmetries, we cannot just add things to our statements. So for that reason, we reviewed how the symmetry derivation could be done. We rederived it in terms of variational forms. So let's start again with the equations of motion for some ordinary level 0 symmetries. You start with the action and you vary the action with general variation that gives you the equations of motion. So here you yeah, you just vary the action. The action is an integral and trace over some field polynomial. You will transform one of the fields, or you just vary by one of the fields, and you put this sort of variational form in there as a placeholder, and that would be the variation of the action. So you see, the variation of the action gives you all the equations of motion times these variational forms. It's like a dx in ordinary differential forms, but here for variations in field space. So in that sense, the equation of motions, the variation of the action summarizes all the equations of motion in this form. Now, you can apply this also to a symmetry statement. The invariant statement for the action is that the action is, well, the symmetry generator annihilates the action. And this is a statement which holds off shell. It must hold whether or not the equation of motion hold here. And because it's off shell, you can vary it again. And if you vary it, you will get a statement like this one. And this is precisely this covariance statement for the equations of motion, in the sense that, well, you have the transformation of the equation of motion plus some other terms, which, once you vary something, you get two terms, and the other term gives you something which is proportional to the equation of motion, like this one, but with certain coefficients here. And these are the asterisk coefficients that I told you about earlier. So so that gives you a precise covariance statement for any symmetry that you can treat in this way. One thing is also clear is that this term here, I mean, you can view this as exterior derivatives or variational derivatives, and since the squared variation or the squared exterior derivative is 0, you can come up with a cohomology. And in this case, this just tells you that the equation of motion covariance is exact basically by construction, because you just write it as a variation of the invariant statement. So this is just plain ordinary quantum field theory in a somewhat formal way, but you can apply this now to Yangian symmetry, where we do have the covariance statement for the equations of motion, which roughly takes again this form here, and we want to integrate it to an invariance of the action. Now, the integrand, it happens to be closed in the variational, it's a closed variational form. Well, maybe you have to add some level 0 variations to it, but you can come up with a closed form for it. If this is closed, then you can apply variational cohomology and hope that the cohomology is trivial. That is, this is much like the de Rham cohomology. There's nothing fancy going on, even for polynomials, certainly not. Even for ordered and for cyclic polynomials, you don't get something non-trivial in the cohomology. That is, if this form is closed, as it turns out to be, it's also going to be exact. And if it's exact, you can integrate it. Now, if it's not exact, you could also integrate it, but then it would depend on sort of the integration path. Wouldn't really make sense, but as an invariant statement. But once this integrand is exact, you can integrate it and you get a unique invariant statement, and that sort of justifies why this is a good statement to look at. And we can then now apply this to twist-deformed Yangian symmetry. And the selection of proper symmetries in this procedure is clear. Basically, all uncharged equation of motion covariance state terms happen to be closed, and they give you a proper symmetry. They are closed because you can use this twisting procedure to obtain them. But all the charged equation of motion covariance terms, they are not closed, and thus they're not symmetry. So if you take a symmetry that has a charge that is outside the subalgebra, then the covariance statement will not be closed because you cannot derive it through this twisting procedure, and thus it's not a symmetry. So And that's good because it just tells us that you have to restrict to all the, just to restrict to the uncharged subalgebra. All proper level 0 symmetries are then local, and the bilocal symmetries, however, do have some deformations which are funny. And for that, let's consider the level 1 momentum. The level 1 momentum is also known as the dual superconformal symmetry, and yeah, it takes a universal form for conformal theories. It's a combination of the rotations and the translations. The bilocal terms are from rotations and translations and scale transformations and shifts. And well, here we have supersymmetry, so also the supercharges Q2 bar contribute. However, now things split into this uncharged subalgebra, which basically has Q4 as the one remaining supercharge, whereas the other three supercharged combinations, they are in principle still there, but there's this additional term that causes a bit of headache also later on. So the nice thing is that all of these, by construction, all of these level 0 generators here are uncharged, and nothing much happens through a twist there. But this term here is heavily affected by a twist, and so you act with these two charges on two different positions of your spin chain or your polynomial. And then you get certain twist factors which are different from sort of the inside and the outside. So there is a different phase before, between, and after the two charges that you act. And this is given by such an expression here. And the nice thing is that the region before the pair of charges and the region afterwards has the same twist factor. And that is essential for making it a cyclic combination. I mean, using it in cyclic combinations, because in cyclic polynomials, the beginning is the same as the end. And thus, if you have different factors, it would never work. But if you have the same factor, it works. And that's why you have to restrict here in these generators to the SU2.2/1 uncharged generators, even for level 1. So that's something you need for compatibility with symmetry. How am I doing in time? While you figure that out, I'll just continue.
15, 20 minutes.
Oh, great. Yeah. So, okay, that concludes the Yangian symmetry for fishnet models, and the conclusion would be that all the uncharged symmetries will probably be symmetries, but all the charged generators of PSU2.2/4 and the level 1 Yangian copies of them, they will not be proper symmetries and cannot be used. But keep in mind that you do need some of these level 0 symmetries to act or to define the action of the level 1 generators, which is a bit of a complication. Let's now address fishnet models. Fishnet models, as a reminder, is a class of conformal and integrable models with a vastly reduced complexity of interactions. So in possible models, you have quite complicated or delicate sets of interaction terms. In the fishnet models, that is much reduced. In that way, they also avoid some of the QFT divergences. However, at the price that the action is complex, and thus it's not really a unitary model. Maybe it doesn't disturb us too much, but of course, in terms of physical models, this doesn't make too much sense. But what's important is that these models are typically obtained as a limit of twist-deformed models. So you can reduce the complexity of n equals 4 super Mills by doing a twist deformation and then taking a limit, and somehow this limit drops out certain terms. I'll again focus on the n equals 1 version of which is obtained by a beta deformation. So in this model, you just have three supermultiplets, three chiral supermultiplets. So they correspond. They're composed from two scalars and two fermions. One scalar and one fermion, but three generations of them. And Right, this is a plane model. Yeah. And the interactions are arranged in a certain funny way. In particular, I mean, these are just the kinetic terms, but here there's a certain cyclic ordering of the indices. So whereas in n equals 4 super mills, you would have all terms where these three indices would be different. Here, you need them in a certain cyclic ordering, and the conjugate of this thing here is not quite this term because this has the opposite cyclic ordering. So in that sense, it's not a real mode. So I'm going to use some sort of cyclic summation convention where if I say A, B, and C, I mean 1, 2, and 3 and cyclic ordering, but not 1, 3, 2. And there's even a simpler version of such a fishnet model where you just have two scalars. This requires you to do a more single limit, and for that reason, I want to skip it here, but would think with some more elaborate thinking, you can come to similar conclusions there. But also, I like this. I like that in this model you have some part of the supersymmetry intact, so it has a bit more structure, perhaps. So what is known about this model? Well, in terms of Yangian symmetry, correlators were shown to have this Yangian symmetry. You have a correlator of some fields at different points in space-time, and you'll impose also the planar limit. That is, you have a certain ordering of these fields around your trace. Then the question is, well, I mean, it's translation invariant, so the level 0 momentum generator would annihilate this, of course, but what about the level 1 translation generator, where you basically apply this rule there to act on two fields within the correlator? Question is that a symmetry? Well, there's one obstruction towards it, and namely that is cyclic symmetry. A correlator cannot really be invariant under such a level 1 generator because it's cyclic, and this cyclic symmetry is not compatible with the bilocal symmetry action of p hat, and that's because the dual Coxeter number for PSU 2.2/1 is not 0, unlike the one for PSU 2.2/4, and that is basically because you have these extra terms here. So the dual Coxeter number comes from a consideration of this whole thing here. If you take everything, the dual Coxeter number would be 0. If you just take the first three terms, it's not 0. And if you use that to define your Yangian symmetry for correlators, you're in trouble. However, you can restore that problem by using some evaluation parameter shifts. That is, if in addition to how you normally act, you add certain contributions where you act with momentum generator on any of the external legs, you just have a shift transformation there, with certain coefficients that you have to adjust to your charges, then you can actually restore this symmetry. So in that sense, you can get Yangian symmetry for correlators in this model. The question is, or a question that we had, of course, was how does this invariance follow from the symmetry? Or can you make it follow from the symmetry of the action? And then what about these coefficients CK? How does one incorporate those? Well, we know that the fishnet model arises as a limit of this twist deformed model. The limit is sort of singular. You send the twist parameter beta to infinity. You send the coupling constant to 0, but in a certain way, and in such a way that you have one remaining effective coupling constant. And it does result in exactly that model. This model here, but with one additional term or two additional terms. These are kinetic terms for decoupled n equals 4 super Mills multiplet, a vector multiplet, but it doesn't interact, so you may as well drop it. Yeah, all the interactions with rest have been suppressed by this limit. So, but it's important for our considerations because the symmetries will be based on such terms. So, yeah, the uncharged level zero symmetries actually have a smooth limit. So whatever remains for the uncharged transformations is just a plain limit. And they also map physical fields to physical fields, and I'll call these spectator fields. They map spectator fields to spectator fields, so they don't mix up stuff. They remain as proper symmetries. Also, the local level 0 2.2/1 remains. But the other Q and Q bars, the ones with indices, they map between physical and spectator fields by construction, and they have to. And that's a bit of a problem, essentially, because the level 1 symmetries do include them. So in principle, however, we may investigate what happens in the limit of such level 1 symmetry generators. So here are the symmetry generators. The original ones, even the deformed ones, are composed from two types of terms: the subalgebra terms and those extra off-diagonal terms, if you wish. The subalgebra is just a plain ordinary level 1 momentum in focus 1 symmetry. And as I said, all of these terms here have benign limits. There nothing fancy happens. Also, since they are bilocal and there are no phase factors involved, yeah, you get no problem. So if you act with this one on the action, you'll obtain a couple of terms which actually have this form here with certain coefficients. But then there's the extra term that you need for the proper symmetry statement, and there's a problem. Well, first of all, these map some spectator terms in the original action, that is these terms here. They are free, but nevertheless, in principle, you can act on them to the contributions of this physical invariant statement. And also, even worse, is the phase factor for the region between those two insertions is a phase factor, and it's a non-trivial phase factor, and the phase factor goes to infinity. So you get some divergent contributions from it, which means that, well, they will not be a problem, but they can reinforce terms which are suppressed, right? So it's a balance of powers, and some terms may survive this limiting process. So some suppressed terms in the original action can contribute to the physical invariant statement, which is bad because you want your symmetry statement to just be derived from the limiting model, not from where this may come from. You want to make a proper symmetry statement in the fishnet model and only that. So this procedure has therefore some limitations, and some terms really cannot be expressed within the fishnet model. Right. So in fact, here's how. Okay, thanks. Here's how these contributions. Well, what kind of contributions you need from this extra symmetry term? So you can act on the actual fishnet model action. And this produces some terms which do contribute, but then there are also other terms which here I mean the term that is suppressed by two orders of this limiting parameter, but since you also have regions of phase factors which can be divergent in the limit, the contribution of the two will give you contributions which are terms of this type here. And then also there are some terms which you certainly cannot express. These are again suppressed. These are cubic terms involving the gauge field and the gauginos. Yeah, these terms exist in the limiting process, but they don't exist in the limit. So the question is, can we keep such a term somehow in this model? We would have to restrict to physical contributions by force, that is only those. But even that is a bit funny because there are some non-local factors in such a term here, which typically act as a selector. They just tell you whether whether or not you have a certain contribution, and you have to avoid the singular ones. So it's sort of a bad thing. It certainly suppresses or misses those contributions from these terms. In that sense, it's not really an honest representation of the original terms. It's more like an ad hoc attempt. If you do it, you will get some contributions from these terms, but the coefficients are much messier than before. And you even wouldn't know how to represent this on correlators. You would have to represent that at the end of the day also on correlators. But if it somehow introduces unphysical fields, that wouldn't be helpful. So, yeah, and some terms like these would not. I mean, you can represent them in this n=1 fishnet model, but certainly not in the biscalar fishnet model, because this is a supersymmetry. It translates between bosonic and fermionic fields. You stand no chance. So thus, we need to compensate otherwise, and the goal is somehow to reproduce the terms that you get from the subalgebra. What's clear here is you should depend only on the symmetries and on the fishnet model as it stands as input. You should not use the limiting process. The procedure should also apply to the equations of motion, not just the action. That might just give us some additional clues. Coefficients of the residual terms are not actually wild. The ones that you get from here, they are not so wild. So maybe there is a way to reproduce these terms. Right. You also see some equation of motion appear in those, so some d dot psi rather than some combinations acting on the derivative on the side. But this is just taking a trace of the derivative acting on the fermionic field. So maybe that's a hint. One may have to adjust the local contributions of p hat. One should also retain to the parity inverting nature of p hat. P hat sort of has this, what changes somehow the parity of your model, so somehow that excludes quite a few terms. But the goal would somehow be to reformulate this q bar term, this additional q bar term, as evaluation parameter shifts, which are ck, pk, which can be represented in the fishnet model. Question is just how to perform this transformation, whether it can be performed or at least somehow argued. However, one could not possibly account for one of the terms that arises here, like particularly this term here, could not come through a derivative acting on something because there's just no derivative in this term. Somehow you'd have to get rid of it. But in fact, it may work that if you change the local contribution of p hat, you'll actually remove this term, and what remains in the rest might just be these evaluation parameter shifts, and that's something of yesterday after midnight. So it seems to work, but yeah, let's see. This is the story to be continued. But I'm hopeful that one can find a rule, and in fact there are rules for determining these CKs, but also somehow to make these local shifts of evaluation parameters work for invariance of the action. So here's my summary of this talk. We've discussed Youngian symmetry for twisted-formed models. First of all, I've presented a clearer derivation for the symmetry of the action in N=4 super and Mills. A bit more convincing than more ad hoc derivation we had before. We then identified Youngian symmetry for twist-deformed models, which is simplest it could be. Basically, you twist-deform all the symmetry statements, and only those that you can twist-deform properly are those that actually survive. So we get a subalgebra, and then we've investigated Youngian symmetry derivation for fishnet models, and still needs to be seen how these residual terms that are not really representable in the limit can be transcribed to something that works purely within the fishnet model. Thanks.
Thank you, Nicholas, for a nice talk. Questions?
Can I ask first a question to the organizers? Are we to ask questions during the talk or just save them all for the end?
Oh, no, please ask questions during.
And then secondly, this one for you, yeah. So should I interpret this statement as saying that the integrability of the twistor form model is broken, or if not, how do you reconcile having less symmetry?
No, I mean, the symmetry is there. You still get a Youngian symmetry. It's not quite as big, if you wish, as the original one, but it's still there. So, and if it's there, well, but okay, it's true. You get a smaller amount of symmetries that are applicable on the one hand, but on the other hand, it's still somehow there in complete form for the equations of motion. Now, if you think about a quantum field theory, maybe you think about Schwinger-Dyson equations. Schwinger-Dyson equations are equivalents of the equation of motion, and Ward identities or Slavoj-Taylor identities are based on Schwinger-Dyson. So maybe the symmetry is there, but I mean, it's not so clear to me why precisely the availability of a quantum algebra for this model as a symmetry makes it integrable. Or what's the precise translation? Is the existence of this quantum algebra, is that a consequence of something simpler? Maybe a simpler statement that just is called integrability. However you formulate it, and then you apply symmetry to it, and thus you get this Youngian symmetry. Or whether you start with Youngian symmetry and then you can, well, then certainly you can derive certain things about like scattering processes, factorized scattering, and so on, that are specific to integral models. So can't really tell.
Can I ask? Goes a little bit against what you just what you said, but what is known about sub-Youngians of Youngian? I mean,
well, I mean, this is it's a bi-algebra, right?
Right.
So a subalgebra is a subalgebra. I hope everyone knows what a subalgebra is and what the consequences of that are. But of a bialgebra, as you've seen, there are additional terms.
But is there? I mean, so you can find say, quantum affine algebras of quantum affine algebras. So you can construct such things.
I can do what? Sorry.
You can sort of construct quantum affine algebras of quantum affine algebras.
Yes,
but and the Youngian, I guess, is a limit of, or can be constructed as a limit of that. But
it's a sub-algebra. It's a subspace of the algebra, but the whole algebra does not exist in the subspace.
For the Youngian.
Yeah, I think that's very generic. And then often there is a way to reform. I mean, to change these additional terms, like we've seen here, into some other terms. For example, if you go from a spin chain to a scattering picture, sometimes the additional terms in the Youngian action, which are, if you reduce the Youngian to the Youngian that keeps the vacuum invariant, that again reduces it to a subalgebra, and the additional terms are translated into evaluation parameters again. So of the Magnon rapidities. So this thing is not completely unknown, but it's not a sub bialgebra. That probably doesn't exist, but maybe you can work with ideals sometimes. That was our own story at some point.
Do you have any comment on how this could apply to twists of the sphere, like a twist of SU4 rather than orbifold of the sphere rather than twists? So that's also integrable, and it also has some.
No, but as always, there needs to be some work for you left to be done, right?
Okay, Kostas, and then Tim, and then we'll break.
Yes, I think at the beginning of your talk, you mentioned beta and gamma deformations, for which the geometrical background as a deformation of IDS5 process 5 takes a very explicit form.
Yes.
Where beta and gamma parameters appear very explicitly. In the deformation of the Youngian algebra, you also have some sort of expressions where beta and gamma also appears. I don't know if you actually talk about this, but since you mentioned it,
I'm not sure I understand the question, but this twist deformation, Drinfeld and Drinfeld-Rashid twist is a very specific form, but it's all based purely on algebra. So
but does it cover the beta gamma deformation?
yeah.
So that means the deformation of the algebra should encode the parameters.
Yes.
Okay.
Yeah, but I mean, okay, one thing you could say here is that this the way this symmetry acts is not, it's not completely common, so it's not the usual story, and it's a question of how much this applies, and you always have to deal here with cyclic states, cyclic objects you act on, and that causes problems. But I'm not sure I understood the question.
Okay, maybe.
I wanted to ask whether this is like, I mean, you are just focusing on on abelian twists in the SU4.
Yeah.
I wanted to ask you if, like, this is to which extent this is necessary for what you did. Whether you can also apply to twists in the ADS part, for example, or also taking non-abelian twists.
Yeah, good question for both. I would say I can probably, I mean, since this is all just algebraic, I could probably apply it to twist in the ADS5 part. I don't see a major obstacle except that there is the interpretation of the gauge theory model. What do you do with that? Well, yeah, string theory might be easier, but gauge theory, it's probably just what you get by twisting, and the procedure works. But our main concern here was that we didn't really understand the procedure too well. So we thought about not adding extra obstacles with messing around with spacetime in the gauge theory setup. But I think it should work. Now for non-abelian twist, yeah, I don't know. The odds are, I mean, if you can formulate things as a twist, it might work, but yeah, things are non-abelian, and then may depend on the fields or non-linear stuff enters. If you probably do it properly, it may work.
I think Nicholas is around, as he told you, for another couple of talks. So if you want to attack him, you have lunchtime, and
If you want to attack, you just get lost.
no, if you want to discuss with him. Yeah, so let's thank Nicholas again, and